So, hello everyone. I hope you can hear me well and you can see the screen also. So, I'm Vaidehi and I'm an assistant professor here at IUCAA. And for next 1 hour or so, we'll be talking about gamma ray astronomy. This is the highest form of electromagnetic radiation. Okay, so as we all know that gamma rays are the most energetic form of electromagnetic radiation. And typically when we say about gamma rays, this means we are talking about energy greater than 100 kilo electron. Okay, say up to 100 kV, 200 kV, we say it's a hard X-ray, but if you go more than that, then we usually call it a gamma. Okay, so in this diagram, you can see this is somewhere here we go on the left hand side. This is the gamma ray band. So the frequency increases. And I don't have to tell you that gamma rays cannot directly reach Earth. They are absorbed by our atmosphere. So for the gamma ray detection, we mostly use space. Though there are some ground-based facilities which use some secondary techniques, which I will discuss later. Okay. So why gamma rays? Why one should study gamma rays astronomy? Okay, so typically when we talk about our the world which we see from our own eyes, looks very beautiful, very pretty, like from the optical band we see nice pictures and all. If you go to remote places, most of these pictures you can see from your own naked eye. You don't need any exposure based camera or whatever. But when you go to high energy band like X-ray and say more in say in the gamma ray band, so since gamma ray is the most energetic form of the electromagnetic radiation, so the corresponding radiative processes that are responsible for these gamma ray emission, they are also very extreme. Very exotic events happen in the universe that lead to the emission of gamma ray radiation. So if you are interested in studying the most extreme events, most energetic events, then you should come to gamma ray. I will give you one simple example that there are some of the gamma ray emitting sources that emit more energy per second than that radiated by our sun in its entire lifetime. So that can give you some idea about what kind of astrophysics we are talking about here. Okay. So with this much introduction, let us start with the gamma ray production mechanisms. So what are the different processes that can give rise to gamma rays? Okay, so in nature, typically this happens via radioactive decay, where the radioactive elements decay into another element, and then along with that, they also release gamma rays. Okay, for example, as you can see some examples here. Other than that, cosmic rays. Cosmic rays, I'm sure all of you must be familiar with this. Cosmic rays are nothing but very energetic protons and some other particles. You can say leptons as well as hadrons also. They are very extremely energetic particles, and then they interact with the atmosphere, and then they generate say a cascade. It's a shower. So in some time that also lead to the emission of gamma radiation. In the nature that happens. Gamma rays are also produced by nuclear fission as well as fusion, and also via neutral pion decay. So these things happen artificially also. Like a human has developed techniques for nuclear fission and all. We all know that. Other than that, there is a there is a technique called, there is a mechanism called Bremster law. It's a German word, which means breaking radiation. So what happens in this? These extremely energetic electrons, when it comes in under the influence of a atomic nucleus or a molecule, so what happens is trajectory gets modified. Okay, and due to this event, when it starts changing its direction, the motion becomes accelerated, and we all know that accelerated charge particle emits radiation. Okay, so in a very simple term, that's how gamma rays can come out from the Bremsstrahlung process also. But this is a very general term. Bremsstrahlung can have different types: thermal Bremsstrahlung, magnetic Bremsstrahlung, and all. Okay, so in this case, in Bremsstrahlung, the released energy in the form of gamma rays, so the energy of the gamma ray photon is typically of the order of the energy of the electron. Okay, there are some other processes where the say Protons also radiate gamma rays, say, via synchrotron process, which is called proton synchrotron. But as you know that protons are pretty heavy particle compared to electrons. So very high magnetic field is needed to make protons start radiating synchrotron emission. But it happens. Okay, especially say in the case of pulsars or say neutron stars and all. Then protons can also interact with different types of photons and can give rise to say pion. Then pion can decay into muon, and then they also release neutrino as well as gamma rays and all. So this means there is a cascade of events. I will briefly discuss some of them later. So gamma ray can emit via these cascades also along with protons and photons. More commonly in astronomy, we usually prefer electrons to radiate because they are low mass particles relative compared to protons. So from energetics, they are more physical as far as the radiation is concerned. So gamma rays can also be produced via inverse Compton scattering. So I'm sure everyone must be familiar with this term. So if or not, then Compton scattering. In Compton scattering, what happens? High energy photons interact with a say low energy electron and transfer some of its energy and loses. In the inverse Compton scattering, the reverse of this happens, where there is a low energy photon and it interacts with the extremely energetic electron or say relativistic electrons and it gain energy. So say, for example, in an optical UV photon, after interacting with a relativistic electron, can become a gamma ray photon. So this is a very efficient process to produce gamma rays. Okay. So I have briefly explained this. So you know that low energy photon enters electron and can become highly magnetic. Okay. So in this case, the energy of the gamma ray photon is proportional to the gamma square, where gamma is the
We cannot hear the voice.
no, there is nothing from my side. What is happening? Like in the background, you are listening something, or maybe if others speak, anyone has kept his mic switch on, then maybe they can switch off. Even I have switched off my fan in my office, so that is also not making any noise. Okay. So I was talking about the energy of the gamma ray photon after inverse Compton scattering. So this is proportional to the gamma Lorentz square. Gamma basically this tells us this is the dimensionless. You can say it's a type. It's a kind of energy of the relativistic electron. Okay, this is representation of the energy of the relativistic electron. You can see the energy of the photon before interaction can get upscattered by gamma square. Typically, gamma is of the order of say it can be as low as say 5 or 10, but it can be as high as 10 to the power 4, 10 to the power 5 also. So you can say if the energy of the photon is say 10 to say if the frequency is say 10 to the power 14 hertz, that is it is an optical photon, and if gamma is say 10,000, so the energy of the photon after inverse Compton scattering will become 14 plus 8 22. It is reaching in the gamma ray band, MEV energy. If it returns to 6, then it will become even higher. Okay. Gamma Lorentz can be given by this expression where the V is the velocity of the electron. Right. Now, after learning briefly about gamma ray production mechanism, let us talk about the gamma ray detection techniques. So, unlike any other band, like say in optical UV or in radio or in near infrared, or say even in X-rays, we cannot directly detect gamma rays because the gamma ray photons are extremely energetic. They can directly penetrate the detector. So that's why directly we cannot, like in optical we see nice pictures. We can directly see some galaxy, etc. In gamma ray band, this is simply not possible. Okay. So what one has to do? One has to convert somehow gamma rays energy to kinetic energy of electron, and then try to detect or say track that electron. This is means via a secondary technique. So this means we have to understand the interaction of gamma rays with matter. Okay. So you know that these gamma ray photons can interact primarily via three processes with matter. First is the photoelectric absorption. This is the primary source of like a primary mechanism of interaction of gamma ray with matter below say few hundred keV. So as we know that what happens in this case when the gamma ray comes and photon comes and it interacts with an atomic, say, molecule also, and it just kicks off on, it gets absorbed. So you know that at that certain the cross section of for this absorption, that certainly happens at the ionization potential of that particular material. Okay, so this method is effective below few hundred keV, where photoelectric absorption happens. At slightly higher energies, say between say few hundred keV up to say few MeV, the primarily gamma rays interact via Compton scattering. See, this does not mean that above 300 keV or so there is no photoelectric absorption. This means the the cross section for this photoelectric absorption is minimal, so almost negligible. Similarly, here in, as you can see in this Compton scattering also, this at lower frequencies, this Compton for the Compton scattering, the cross section is, this is called Thomson cross section. It is a constant. But as you go to higher frequency, that means as the energy of the photon increases, above say around 500 keV or so, the cross section starts decreasing, because this interaction of gamma ray and with matter starts happening in the quantum regime. So the classical limit breaks when the energy of the photon is very high, and we start reaching to the Klein-Mishner regime, which is the quantum effects take place. That's why Compton scattering also it's a good technique to detect gamma rays below few, say up to 500 keV, up to say 1 MeV, also, not beyond that, because where after that the cross section decreases sharply. Above that energy, gamma rays primarily interact with matter via pair production. This is a very efficient technique. It happens above few MeV, and it goes up to GeV and TeV energy range, where you can say this interaction starts happening around 1.02 MeV, as everyone knows this, and then cross section increases after that. Okay, so there are the three primary techniques of with which gamma ray interacts with the matter. Okay, now let us briefly talk about the problems that one faces when try to detect gamma rays from space. Okay, first of all, low number flux. That means the sources are very, very faint in gamma ray band. Okay, just to give you an idea, the typical flux level of a bright gamma ray source is of the order of 0.001 photons per centimeter square per second per MeV. And this is for a bright source. If you go for a moderately bright or say faint source, this becomes 10 to the power minus 6 and to the power minus 7. So the number of photons that we receive in the gamma ray are very, very small. So what we have to do, we have to go for a very longer integration time to measure a significant signal. Okay, so longer means of the order of few hours to days to get a significant detection. In fact, when we study some gamma ray source, I will briefly describe later that in some cases we have to integrate the data of the order of few weeks to get a say 3 sigma or 5 sigma detection. The sources are so faint in gamma ray band. Okay, and very briefly talking about the sensitivity limit for the detection of a source. Say we want to detect the source at 5 sigma confidence level. So 5 sigma means 5 times what? Sigma. Where sigma is the standard deviation of the background gamma ray. So this means above the background, how significantly we detect the source. Okay, here you can understand from this slide itself. Your slide, you can say this the background color of the slide, which you see from white to grayish to black. This is our, say for example, this is the background, and you are seeing these sentence or say words. These are above the background. In the same fashion, we calculate. So we have to calculate the sensitivity. Okay, so this sensitivity can be given by this expression. So rather than worrying about this complex mathematical expression, I just want to tell you, see DFB by DE, this is the background gamma ray flux. So you see, if the larger the value of the background gamma ray flux, larger the value of the threshold. Okay, so this means if you do calculation for a certain value of DFB or DE, say F minimum comes say 10 unit. So this means you cannot detect anything below 10 unit at say certain say 5 sigma confidence level. Okay, but if the background is low or somehow if you can reduce the background, your F minimum will decrease. So this means say F minimum after decrease, somehow it has become 5 units. So you can detect the sources down to 5 units. So this means you are going for the deeper sensitivity. Okay. Similarly, A effective is the effective area of the detector. Okay. So larger the effective area, smaller the value of FU, or say deeper the sensitivity. That's why people means when satellite is launched, they always try to have the effective area as large as possible. And T OBS, which is the integration time. So you can see the larger the integration time, you can go for the fainter sources. The sensitivity will be deeper. Okay. Now, there is another problem with the gamma ray detection in space is the high background from cosmic rays. You know, cosmic rays are coming from all the directions in the space. And these are highly energetic particles. They constantly bombard the detector. So instead of detecting only gamma rays, you are detecting everything. So how to discriminate between the background and my source? Your detector does not know anything. It will detect whatever is falling upon it. Okay. There is another problem of the collimation and source localization. See, unlike like in optical astronomy where we can put mirror or say lens to focus optical say rays or optical photons to say focus point, and you can get the image of the particular object, etc. Okay, but in gamma ray band it is simply it's not possible because gamma ray are highly penetrating. They cannot be collimated. So we have to go for secondary techniques. Okay, but what people do, they try to do something. They have developed some innovative ideas because without collimation, it is simply not possible to identify a gamma ray source. Means yeah, you are seeing some gamma ray detection, but we do not know what is happening, where it is, where exactly it is. And without the positional information, how we can do physics? So there are some solutions where you can see there's something called passive collimation, where what you can do, you can shield the detector from say all sides except a very narrow cone, and then allow the gamma rays should come only from that cone. So what happens? That this means you know that whatever the gamma rays are coming, they should be coming only within this cone region. But still, this cone is not a small area. Typically, this angle of the cone is of the order of few degrees, which is very large. So we cannot get any directional information about sources which are within this cone. Outside the cone, anyway, you have shield. Okay. Then there is something called occultation technique, which you would have heard more about when people talk about exoplanet detection. When there is an exoplanet coming in front of a star, and then the starlight dims, and then you can do whatever different types of science. Similarly, say for gamma ray source is lying somewhere away from Earth, and we are observing, say the satellite is orbiting around Earth. So you know when you are somewhere here, then you are detecting emission both from the background. Background means anything other than source, as well as source. So you have some flux. But as the satellite comes behind Earth, so your source is occulted. Okay, so you will see only background, and after some time again, as you will go, then again you will start seeing source plus background. Okay, so this means from that you can calculate the source flux. So this technique was used earlier 1960s or 70s when people try to some quasars where they will try to adopt this occultation technique by using moon and then calculate the positional information of that particular object. Okay. Now recently, in the last 2-3 decades, the concept of coded masks have appeared. In the coded mask, it's simple as the name suggests, there is a mask which is just coded. Okay, so since the people who have built this coded mask, they know the pattern of this mask. So you know that from a different direction, when the light is coming, or say gamma ray photons are coming, they will, and there is a detector below this coded mask. So from different direction, they will make different types of shadows, and this we know a priori. Okay, so different shadows for different directions. Now these patterns can be unfolded to compute the distribution of sources. We can derive the positional information. Okay, that okay, given a certain pattern, which direction these photons are coming from, we can derive the positional information of the source. Okay. Now there is a more advanced technique where the tracking of the trajectory of secondary particles. This I talked very briefly earlier. Is that suppose a gamma ray photons are coming and then we have a charged particle anti-coincidence shield. This means this shield will protect the detector in such a fashion that charged particles will not enter here. Okay, so this way you can avoid cosmic rays. Not 100%, but mostly. And these gamma ray photons will come. They will interact with pair conversion foils, and then they will produce pairs. Electron, positron. If you have a semiconductor, then there will be electron and hole. Okay. Then what we do, we try to follow the trajectory of these secondary particles. Okay. So we have a calorimeter at the bottom. Calorimeter measures the energy, and then when we from the tracking detectors, we can trace back the direction from which the electron positron pairs are coming, and from that we can track the direction of the gamma ray photon. Okay, so we can get both positional information as well as energy of the gamma ray. So, and this technique is developed, and several detection techniques are developed based on this principle of tracking the trajectory of secondary particles. For example, scintillation technique. What happens in this? Gamma ray produces electron hole pair, and this electron hole pairs, after what happens, it recombines and produces a optical, say typically it's a UV photon, and then what we do, we measure this UV photon. Okay, and from that we can calculate the energy of the corresponding gamma ray photon as well as the direction of the from where this gamma ray photon is coming. Then there are solid state detectors. Again, the principle is same. The gamma ray produces multiple electron hole pairs, and then after combination of these pairs, the optical photons are generated, which we detect, and from that we try to infer the direction and the energy of the. Then there are other spark chambers as well as drift chambers. If you search in Google about these terms, and then you will find they are very simple techniques, but they have been extensively used in gamma ray, specifically earlier days. Okay, like in spark chambers, what happens, as the name suggests, gamma ray produces electron positron pair, and then when this pair goes through the spark chamber, it creates sparks. Okay, and then which we try to, from that we try to detect the energy of the gamma ray photon as well as the direction, and a similar thing that drift chambers. Okay, now so far whatever I have talked, this is mostly for the space-based telescopes, but people have also used similar principle to detect gamma rays from the ground also. But again, as I said earlier, that you cannot directly measure gamma rays on the ground because gamma ray gets absorbed in the atmosphere. So people have used a technique called Cherenkov technique. So what happens in this? Very high energy gamma rays, this method is effective typically above 100 GeV or above. So hundreds of GeV or say TeV energies, where these gamma ray photons, they interact with the air molecules and produce air showers. So photons will interact, then it will produce electron, positron will interact, again produce gamma ray photon, then lots of things will happen. Again, you may have protons also, they will negate pion, nucleon, muon, all sorts of bonds. So in this case, what happens is relativistic particles with energy, where n is the reflection index, these shower, they produce nanosecond flashes of Cherenkov radiation. So you can see this is the front view. Say if gamma ray photon is coming, it starts interacting with the atmosphere and produces a shower. Okay, this shower we see in the form of flashes of Cherenkov radiation. Okay, and then if we have a detector on the ground, they try to detect these nano flashes of Cherenkov radiation. So this is the, you can say it is the bottom view. They say suppose if you are seeing from below, so you rather than seeing only one line, you will see shower. So on the bottom view, you see some elliptical structure. So if you have more than one telescope, you can cross match and you can find the direction from which the original gamma ray photon came. Okay, and using this principle, now there are several imaging atmospheric Cherenkov telescopes have been constructed, and they are in operation. I will show some of them later. So this is also a very useful technique. This is useful specifically if the energy of the photon is very, very high, say up to TeV or even higher. Okay. So now this I have already explained. So with this, so far I have explained very briefly about the different mechanisms of gamma ray production. I have briefly talked about the challenges in the detection of gamma rays. And then also I have briefly talked about to overcome these challenges, how people have developed different detection techniques. Okay, so with this, now let us go to some sort of history. So now we know basics of these gamma ray astronomy. So now we can go how people have started. So earlier in this gamma ray astronomy started in 1950s when there was a, everyone is knowing about the Cold War between United States of America and United States of Soviet Russia. So United States in late 1950s and early 1960s, they launched several military satellites under Vela program. With the idea was that they were scared that Russia might be conducting several covert nuclear bomb testing. So since one of the product of nuclear fission is the gamma rays, so they launched several satellites with the idea that suppose if nuclear blast somewhere happens, it will release gamma rays. So if they have several satellites orbiting Earth, they expect to detect those gamma rays. So the catch was that in this case, you expect gamma rays to be coming from below, that means from the Earth. But when the satellite was launched, what it found, it didn't find so many gamma rays, but it detected few hundred gamma ray events. But what interestingly it found that gamma rays are coming from all the directions, not only from towards the Earth. It is coming from all the directions. So whether nuclear bomb was exploded on all the directions. So this was certainly not the case. So people were perplexed. What was happening? So a few hundred theories were developed for a few hundred events. Late 1960s and earlier 1970s, then specifically for astronomy purpose, some satellites were launched. They started observing the sky away from Earth, and then they detected a few very bright sources of gamma rays. Vela was one of the gamma ray source, I think which was one of the first gamma ray sources detected. So in 1972, SAS2 discovered two pulsars. Okay, later in 1975 to 82, there was one satellite launched in COSP. It detected about 25 objects in gamma ray band. And most of these sources were unidentified. We had absolutely no idea because the resolution of those satellites was very poor. In fact, even it is even very poor even today because of this problem of gamma ray collimation, which I discussed earlier. Okay, so most of the sources were unidentified except one quasar, which was very, very bright. If I recall correctly, it was 3G273. And then other than that, these satellites also found that other than gamma ray point sources, there is a diffuse glow of gamma ray background coming from all the directions. It's like a foggy structure in gamma rays, which was later termed as diffuse gamma ray pattern. Okay, the breakthrough started coming in 90s when competent gamma ray observatory was launched. I think this was one of the NASA's great observatories, along with Hubble Space Telescope and Chandra X-ray Observatory, if I remember correctly, probably. Okay, so Compton Gamma Ray Observatory, it had several instruments on board. Say, for example, burst and transient source experiment, or called BATSI. So, as the name suggests, it was primarily it was meant to detect gamma ray bursts or transient events. So, the detector was built to keep this particular science in mind. Then there was Imaging Compton Telescope. This was gamma ray detection, means this instrument detected gamma ray primarily in the MEV band, and this telescope was built on the concept of Compton scattering. So this means it was working on, say, between few hundred keV up to few MeV. Then the workhorse of Compton Gamma Ray Observatory was Energetic Gamma Ray Experiment Telescope, or called EGRET. This had a wide energy range, say from, if I remember, probably few, say 10 to 20 or 30 MeV up to say 10, 20 GeV. And this was based on the, you can say, pair production techniques. Okay. So Compton Gamma Ray Observatory, when it was launched, so we started learning the true nature of gamma ray science. Though the sensitivity was not very good, but we started getting some idea about the types of astrophysical objects that emit gamma rays. Okay. Say for example, like we detected gamma ray emission from Crab nebula. So we know that okay, so this means pulsars are very strong in gamma. Pulsars can be very strong emitters of gamma ray radiation. Okay. Later in early 2000, when the integral was launched, this was the International Gamma Ray Astrophysics Laboratory. It was launched by European Space Agency. It is still in space, and but sensitivity of this instrument is not very good, and it mostly observes the galactic plane, means the plane of our own galaxy, when there are very bright pulsars, X-ray binaries, and different types of astrophysical objects are lying. Then in 2007, Italy launched Agile. Okay, this name is in Italian. I cannot tell you the full form because I even don't know. Astro Rivaliere. So it was launched in 2007, and this has a wide coverage, say from 100 MeV up to say few tens of GeV. But the real breakthrough happened when Fermi Gamma Ray Space Telescope was launched in 2008. This is the best gamma ray satellite ever launched in space by human being. So this has a very large energy coverage. This has two instruments. One is the Large Area Telescope or LAT, which is the main instrument on board for me. So you see, this energy is a 20 MeV. It goes about 2 TeV. TeV is behind the picture. Okay. So you can see how many orders of energy or how many orders of coverage it is coming. MeV to GeV, GeV to TeV. So you see two orders of, if you include gamma ray burst monitor, which is primarily meant to detect gamma ray bursts. It has coverage from few hundred keV up to 30 MeV. So overall, this satellite has energy range from few hundred keV up to TeV energy. So this is 3-4 orders of magnitude. So this is probably the only satellite with such a wide energy coverage. Okay, and this instrument, again, you can see some schematic here. It is primarily based on the pair conversion concept. Gamma rays are coming, they will interact with the pair conversion foils and they will produce electron positrons. Then we try to detect those electron positrons and trace back the direction as well as energy of the gamma ray. Okay, fine. So other than the space satellites on the ground, as I was talking earlier, imaging atmospheric Cherenkov telescopes. There is in southern hemisphere in Namibia, there is a high energy stereoscopic system or called HESS. Okay, this is a system of 4 ground-based Cherenkov telescope you can see here. And then there is a MAGIC or Major Atmospheric Gamma Ray Imaging telescopes in La Palma, Spain. Okay, so these are the ground-based Cherenkov telescopes. In fact, there are many more, Fact, Hawk, Veritas, etc. You can search these names in Google and you can find more information about them. And in fact, there is another Cherenkov telescope named CTA, which is the Cherenkov Telescope Array, which is expected to bring a new, you can say, another breakthrough in the TeV astronomy, like the tera electron volt astronomy. So this is an upcoming mission. So that's all from this one. So we have discussed gamma ray production techniques, gamma ray detection techniques, problems with the gamma ray detection, as well as now we have also learned briefly about the different satellites and telescopes which people are using to study gamma ray sky. So with this, now I have come to the second part of my presentation, which is the astrophysical gamma ray sources. So let us talk about some physics of those sources which are gamma ray emitters. Okay. So first of all, I will talk about relativistic jets. So I'm sure all of you would have gone through the course of active galactic nuclei. So I don't have to tell you what are these AGN. So some of these active galactic nuclei, about 10% of them host powerful relativistic jets. Okay. So what are these relativistic jets? So these relativistic jets are collimated, as the name suggests, relativistic bipolar flow of plasma blobs shooting out of the plane of the accretion disk, like this way. Okay. So I want to give you some feeling about the size and scale and energy of, or say, power of the jets. The typical cross section of a jet, you can imagine it's like a cone. Okay. So the typical cross section is of the order of, say, typically it is one light day. Typical. Now, you know that it varies from this as you go away from the galaxy, but typically it is one light day. So one light day means the time, the distance that light will travel in one day, and light travels with 300,000 kilometers per second. So you can get the size, the vast size of this cross section of the jet. Okay. Now, typically these plasma blobs which travel along the jet, they typically cover the entire jet cross section. So you can get the idea. You can imagine like a sphere which are rolling along the jet and covering the entire jet cross section. So you see, that means plasma spheres with a diameter of the order of one light day, how big it will be, and then it travels with velocity close to speed of light. How, from where they get so much power? Okay, so you can try to understand. That's why I told in the beginning, when we talk about the gamma ray or high energy astrophysics, we are talking about the most extreme events in the universe. Okay, so what happens in this plasma? This is confined by the strong magnetic field. So strong magnetic field, you can imagine magnetic field lines are of the shape of a helical structure. You can say like this, and then plasma blobs follow these magnetic field lines. Okay, that's how this jet remain collimated. So what happens? This magnetic field try to compress the plasma inwards, where the pressure of the plasma try to go outwards. So as far as we have a balance, the jet remain collimated. But you know that as you go away and away from the black hole, slowly, magnetic field will decrease. So this means slowly, plasma will start expanding. So that's why slowly, after if you see the radio images of relativistic jets, you will find that at the end the plasma starts to diffuse like a water fountain kind of structure. Okay. Now, in this jet, the plasma contains highly energetic electrons and protons. Okay. And what happens, this means there are relativistic particles moving in this plasma, and there is a magnetic field. So, in the presence of magnetic field, you know that the charged particle in the presence of magnetic field, it radiates. So, if the velocity of the charged particle is relativistic, it will emit synchrotron radiation. And you know that if the charged particle velocity is non-relativistic, it will emit cyclotron radiation. So synchrotron radiation takes place in the jet. That's how the radiation comes out. And then there's a Compton, inverse Compton scattering also takes place. How it will take, I will show you later. So that's how the jet radiate emission. Okay. Now there are a few, you that these agents are lying everywhere in the sky. Some will have jet in the direction of sun, some will have jet in the direction of some other galaxy, some have some other direction. But some AGN may have jets that are pointed directly towards Earth, that is, towards the observer. Such AGNs are called blazars. So you can see this is a picture of a typical quasar or say AGN. We have a black hole, this is accretion disk, and these are jets. So this happens typically in the sky. But in some cases, a user might be standing here. So this means the jet is directly pointing towards the observer. So if this is the case, you will see the same quasar will appear something like this. Okay. So in this case, the same galaxy or active galactic nuclei will be called as a blazar. Okay. So now what is interesting about this blazar? The orientation of the jet. Okay. So and this, due to this orientation effect, this has a dramatic effect on the emitted radiation. Because if you recall, I told you that the electrons are say or particles which are emitting this radiation, they are moving with the relativistic speeds. And when they are moving directly towards us with relativistic speeds, there's an effect that takes place, which is called Doppler boosting. So I'm sure if you guys have radiative process class, this must have been taught about what is Doppler boosting. So what happens in this case? Say in the rest frame, suppose if you are standing, you are sitting on that block, radiation will be coming in all the directions. Okay, but if you are standing, say away from the block, and the blob is moving towards you. So what happens? Most of the radiation is confined in a cone. Okay, this effect is called beaming effect. So that's why this is in the rest frame of the blob, radiation is going in all the direction. But in the observer frame, most of the radiation is confined in a cone. So what happens because of this? A faint source becomes bright. So intrinsically the source might be faint, but due to this peculiar orientation, when this relativistic particles are moving directly towards the observer, the radiation gets enhanced, typically by a factor of delta to the power 4. So delta is the Doppler factor, and this has a value, typically it has a value 1020. So you can say typically easily the flux gets enhanced by 10 to the power 4. Okay, so what happens if the source, even it is a faint gamma ray source, if the jet is pointed towards us, it will become very bright gamma ray. Okay, so because of this Doppler boosting, the beamed AGN or AGN that have relativistic jet pointed towards us, they are the most abundant gamma ray emitters in the extragalactic high energy sky. Okay, so if you see, this is a real picture where this is in the center, we have a plane of our own Milky Way. This is a gamma ray picture taken with the Fermi Large Area Telescope. The point sources that you see in this image, more than 90% of them are blazars. Okay, so these are the most powerful persistent source of gamma ray radiation. So now let us briefly talk about the radiative mechanisms that lead to gamma ray emission in these relativistic jets. So you know that synchrotron radiation lies mostly in the radio to X-ray band. This means if the charged particle or say electron is radiating in the presence of magnetic field, the emitted radiation will have frequency mostly in say from radio up to X-ray, mainly radio to optical UV, but up to X-ray also. So, but this means directly synchrotron radiation cannot explain gamma ray emission. So people have proposed that gamma ray emission may be coming via inverse Compton scattering. So the energy, as you saw this expression earlier also, which means the energy of the photon is enhanced by the factor of gamma square, where gamma is the energy of the relativistic electron, Lorentz factor. Okay, so for the inverse Compton scattering, one needs low energy photons and highly energetic electrons. Correct? And we know that highly energetic electrons are present in the jet. In the plasma, they are very energetic electrons are present. So from where the low energy photons can come and interact with these energetic electrons. So let me show you a picture. You can understand this. This is a cross section of an AGN. In the center, we have a black hole surrounded by accretion disk. And then we have a broad line region clouds. That this is a jet, and this is a dusty torus. It's a cross section of a torus, which is basically it's a donut shaped structure. So if we take a close look at any plasma blob, this plasma blob is filled with relativistic electrons. Okay, and I have not shown, but you can understand that there will be like this. There will be tangent this magnetic field. So in this tangent magnetic field, these relativistic electrons are moving, and they will radiate synchrotron radiation. So let us consider this synchrotron radiation, synchrotron photon coming from this electron. So this synchrotron photon is coming. This synchrotron photon may interact with this electron and can get upscattered to high energy, to become another high energy photon. So this means there could be low energy synchrotron photons emitted by the same electron population, and then inverse Compton scattering can take place. Okay, so that's how this inverse Compton mechanism can radiate gamma ray photons. And you see, in this case, since the electron population which is emitting the synchrotron photons, the same population is also upscattering the same synchrotron photon. This inverse Compton is called synchrotron self-Compton or SSC. And people have found that SSC can explain X-ray to gamma rays. Okay, but if you are following me, you can understand there could be photons coming from the torus. There could be photons coming from the accretion disk, or say from the broad line region, or say from the narrow line region also. Okay, so AGN also has these components. They also radiate. Okay, so these photons, say from the broad line region cloud, they are coming, say, from outside the plasma blocks, outside the jet. And these photons also can get upscattered by this relativistic electron population and can become the gamma ray photon. And since in this case, these photons are coming external to the jet, this inverse Compton scattering is called external Compton process or EC process. And it has been found that this mechanism well explains the gamma ray emission from luminous blazars. The blazars in the source which are very powerful, whereas SST can explain gamma ray emission in low luminosity blazars. Okay, I will give you one example of overall picture of this relativistic jet. This on the right hand side, you can see this is the spectral energy distribution of a powerful blazar. Spectral energy distribution means we are plotting the source flux as a function of frequency. At different frequency, you observe the source and note down flux and you plot. You can see the flux is easily reaching 10 to the power 48 ergs per second. So this is a very powerful data. Okay. So in this diagram, this green as well as red data point, this is the observation. Okay. And the lines which are different, you can see this pink color line or say this green dashed line. This is different radiative mechanisms. So you see, it is simple. It's like a black body. So you know, black body is nothing but it's a expression. You know, F equal to 2 h nu cube by c square 1 upon e to the power h nu by kt minus 1. This is one expression. Similarly, synchrotron radiation also has similar expression, though it's a bit complex. Similarly, synchrotron self-Compton as well as external Compton also has different mathematical expressions. So you can solve those equations as a function of frequency and you can plot. So you know the input will be strength of the magnetic field, energy of the electrons, Lorentz factor of the plasma, etc., etc. So this means this is my modeling. Okay, so you can see that that's how we explain the observation. Like in this case, we can see right from X-ray and these, you know, XRT, BAT, UVOT. These are the different instrument on board different satellites. The UVOT is ultraviolet optical telescope, XRT is X-ray telescope. This is a burst telescope. LAT you have already seen. This is a large area telescope on Fermi. Okay, so in this particular diagram, you can see right from X-ray to gamma ray, the entire radiation can be well explained by external or EC process, external Compton. SST in this case has a negligible effect. Okay, so that's how we try to understand. Okay, suppose if we detect a gamma ray photon from an AGN, the gamma ray photon will not tell you that see I am coming from EC or I am coming from SST. That we have to infer from physics. That's how we do that. Another thing you can understand from this figure is that the radiation is coming from very low frequency. You can say 10 to the power 8 hertz. This is after all few megahertz to gigahertz. This is a radio frequency. And you are reaching up to GV, TV energy. And radiation is coming across the electromagnetic spectrum. So these blazars are one of the rarest astrophysical objects that emit radiation across the whole electromagnetic spectrum. So this means if you detect the source in more energy band, this means you can attack more problems. This means you can have better research. You can do many more things. That's why blazars are very interesting objects to do with science. And this plot also highlights the importance of having multi-wavelength observations. Say, for example, if you don't see anything above X, or if you don't have a satellite which can measure X-ray and gamma ray, you will see only radio and optical UV, and you will try to make a physics from this. But you know that you are missing a major chunk of the other part of physics. So it is very important to have as much observation as possible. And this is important not only for blazars, but also useful for general non-blazar type of active galactic nuclei also. So this is called multi-wavelength astronomy. And that's where today's astronomy is going. Okay. Now there is another type of astrophysical objects that emit gamma rays, as the name suggests, gamma ray burst. Where I will go very quickly. I just have 5-6 more minutes, so let us try to wrap up very quickly. So gamma ray bursts. So gamma ray bursts are nothing but extremely energetic, rapid outburst of powerful gamma ray radiation, as the name suggested. Okay. So we detect a GRB first in gamma rays. That's why name is gamma ray burst. But after few hours or so, we started seeing the radiation at lower frequency. That particular object becomes visible in, say, X-ray, optical, UV also, in the sometime in radio also. And this later, whatever observation radiation we see, this is called afterglow. Okay. And GRBs are the brightest electromagnetic event in the universe. So they emit energy typically 10 to the power 52 or 10 to the power 54 or like that. Okay. And this gamma ray burst can last from milliseconds to hours. And these GRBs are having particular two types. One is called long gamma ray burst, where the average duration is of the typically 30 seconds, where the range between 2 to 100 seconds. Means for this particular time, you will detect the source in gamma ray. Okay, and people have proposed that long gamma ray burst happen when an extremely massive star, typically of the order of few tens of solar mass, collapses to become a black hole. Okay, and then when it collapses, it explodes, and that leads to long gamma ray burst. And this event is also called a hypergamy. Then there is something called short gamma ray burst. So where the average duration is typically below 1 second. So it is of the order of from few milliseconds to 2 seconds. So you can easily understand that detecting short gamma ray bursts is more challenging compared to long gamma ray bursts because they are very short-lived events. Okay, so people have proposed that in short GRB, this short GRB happens due to the collision of two orbiting neutron star or a neutron star and a black hole. And I leave you to think why we don't see short GRB when there are two black holes colliding with each other. Okay, but at the moment, let us go ahead with this. So when there are orbiting neutron stars collide with each other, or one neutron star, one black hole, then we see short GRB. They are dimmer than long GRBs, but means they are dimmer, but they radiate more energetic gammas. Okay, and in fact, short GRBs they have got too much attention nowadays because of the gravitational wave detection. Okay, in 2017, LIGO Observatory, LIGO Virgo, they found a gamma ray wave detection, and at the almost simultaneously, Fermi Gamma Ray Space Telescope detected one GRB positionally consistent with the direction of the gravitational wave event. And this is the Hubble Space Telescope image of that particular galaxy where this gravitational wave event happened. You can see this HST image taken 5 days after the gravitational wave detection. There was a bright short gamma ray burst. This is an optical image. Okay. So this also highlights the importance of gamma ray observations in multi-messenger astronomy. Okay. So how gamma rays are produced in GRBs? The concept is very similar to that in AGN relativistic jets. Again, in the both, whether it's a neutron star collision or it's a massive star collapse. In both cases, a black hole is formed surrounded by a material of, say, accretion, which forms a accretion disk, and this system launches a jet. Okay, and in this jet, you have a blob of plasma. Some blob is moving slow, some blob is moving fast. So they collide. When they collide, so the electrons or say the charged part which are moving, they get energy. They become more energetic and they started emitting gamma rays. That's why we see first gamma ray emission from a GRB. Okay, and after some time, as they slowly lose energy and this jet interacts with the surrounding medium, we see afterglow at lower frequency. One can ask why gamma ray emission didn't happen here or even closer to the black hole. Because the emission region is so compact that most of the gamma rays may get absorbed. This emission region may be very opaque. Okay, fine. Now go to another type of astrophysical object which are like a prominent source of gamma ray, which are pulsars. So pulsars are nothing but a compact neutron star where charged particles are accelerated in the presence of extremely strong magnetic field up to relativistic speed. And in some cases, we do detect some pulsars in gamma ray band. So what happens? This radiation is coming in the form of a beam, and whenever this beam passes through Earth, you imagine this is this neutron star is rotating like this. Okay, so it is something like lighthouse. All right. So sometimes we see pulses. of gamma ray emission. So these we detect pulsars in the gamma ray band. Interesting thing is that, like you take the case of Grab pulsar. So you see when there is a pulse in the radio, we see pulse in the optical, we see pulse in the X-ray, we see pulse in gamma ray also. But there are pulsars which show pulse in X-ray, pulse in gamma ray, but there are no pulse in optical. Or at the time there is no pulse in radio. This is a mystery. We do not know why, what is happening. That's why studying these pulsars, this is the importance of multiple astronomy. So this is a very open and very challenging problem in pulsar astrophysics. Okay. Now finally, I will talk about the diffuse gamma ray background. So you know that cosmic rays are coming from all the directions. These cosmic rays can interact with the interstellar gas. What is interstellar gas? Gas present in the interstellar medium. Okay, and these they can interact with the cosmic rays and producing diffuse gamma ray like a globe, like a fog. Okay, and in fact there are some star forming galaxies, mean the galaxies where star formation is taking place at a high rate, say few hundreds to thousands of solar mass per year. So it means lots of star formation means there is lots of star forming material. This means medium is very dense. So their cosmic rays regular continuously interacts with these dense interstellar medium and produce gamma ray flows. That's why some star forming galaxies are have been detected in gamma ray band. In our galaxy, you can see from our own galaxy perspective that cosmic rays interact with the interstellar gas and produce diffuse gamma rays. Then in the novae and the novae supernovae, some there is a production of radioactive material, say 526 aluminum, and the decay of these radioactive material also produce gamma rays. There could be interaction of the matter and antimatter. This is important specifically in the galactic center. So due to this pair annihilation process, gamma rays are produced. So collectively, combining all these things, we see a diffuse gamma ray background. This means from this picture, if we remove these point sources, whatever is left is the diffused gamma ray background. So this is also a very important problem in gamma ray astronomy to understand the origin of gamma ray background, diffuse gamma ray background. And this diffuse gamma ray background can have galactic as well as extragalactic in nature. So galactic means we are talking about our own Milky Way. Extragalactic means we remove the contribution of our own Milky Way, and then whatever is left is the extragalactic diffuse gamma ray background. Okay. So to summarize, what we have learned today, we have learned what are gamma rays. We have briefly understood gamma ray production mechanisms. We have briefly understood gamma ray detection techniques. We have seen some gamma ray space telescopes, the principles on which they work, that also we have seen. And finally, I have briefly talked about the different types of astrophysical objects that are sources of gamma ray emission in this universe. So with this, I have finished my presentation. Let me see if there are any other question, or alternatively, if you want more time, then what we can do, maybe I have given my email address in the first slide. You can write me an email also, but one second, there's some chat window. What? Okay. Okay, I can see one question in the chat window which says, does long gamma ray burst produce a series of continuous gravitational wave till its own depletion compared to a single shot of gravitational wave of short gamma ray burst? Well, okay, so first, so I would say, you see, first of all, as of now, we have seen there are only one example where we have found a gamma ray burst positionally consistent with the gravitational wave effect. Okay, so there are only one we know as of now. So, does long gamma ray burst produce a series that we can say when we detect a few long gamma ray bursts positionally consistent with gravitational wave events? So far we haven't seen. Okay. And I think from the physics perspective also, people have proposed that short GRBs are probably more likely to produce gamma ray, this gravitational wave event, detectable gravitational wave event. Long GRBs may also release gravitational waves, but I don't know whether it's possible to detect them or not. maybe a gravitational wave expert can give you a more accurate answer if you are not happy with my answer. Okay. Okay, now I'll go to the next question. What is the need of several ISCTs in? See, you can definitely detect Cherenkov radiation from one, but if you recall in my slide that determining the positional information is very challenging if you have only one. Okay, only one means you have only one. You will detect only one ellipse of this Cherenkov radiation. But if you have more than one, you can extrapolate the axis of these ellipse and find out where they are cross matching. Yeah.
Oh, I see. So we do some kind of triangulation to
yes,
look
yes,
at
yes,
it.
yes,
Okay.
yes. Oh, fine.
Okay.
Okay. So we are already 3 minutes past the hour. So I would say I encourage everyone. More questions means I was able to trigger some interest about gamma astronomy. Please feel free to write your question in the Google Doc, or please feel free to write to me. I will be happy to answer all of them. And thank you very much for joining. And then please enjoy your lunch, and then we will see next time. Okay. Bye bye everyone. Thank you.